Hi, I'm Heidi Newberg, and I'm going to tell you about the discovery of shell structure in our very dynamic Milky Way galaxy. This is an artist's picture of the Milky Way galaxy. I can't show you a real picture because I can't get out there far enough to get a camera and look down on it to take it. But you get the idea. There's a bar and then there's spiral structure and these big spiral arms. If you take that spiral structure and you turn it on its edge, then you'll find it's a very thin structure and it looks like the blue in the picture. Now we're going to throw in a small dwarf galaxy on a fairly circular orbit, and the gravitational tidal forces of the Milky Way rip the stars off the dwarf galaxy and they spread out into these very long streams which can circle all the way around the Milky Way. And in fact, the stars in these tidal streams become part of what we call the stellar halo of our galaxy. If instead the dwarf galaxy comes in on a radial orbit, then it goes straight through the galactic center and the dwarf galaxy is ripped apart and its component stars go out on radial orbits that go off in all directions. I've been studying tidal streams in the Milky Way halo for 2 decades, and we found this Sagittarius dwarf tidal stream which goes across the sky like this. There's an orphan stream and there are dozens of other streams out there in the Milky Way halo. I've even edited a book on the subject. In 2015, my group discovered that there were ripples in the disk of the Milky Way, as shown in this, again, an artist's picture. The ripples are caused by the dwarf galaxy falling in. So it's not just that the Milky Way galaxy rips the dwarf galaxy apart, but the dwarf galaxy has an effect on the Milky Way of making this wave-like structure, or it could even have caused the spiral structure that we observe in our galaxy. But let's go back to that picture of the tidal streams in the sky. A stream looks like this long, narrow structure in the sky, but what about this kind of blobby Virgo overdensity and Hercules Aquila cloud? Well, if we pick up some stars then from the Virgo overdensity and measure their line of sight velocities, we find that some of them are moving away from us with positive velocity, and some of them are moving towards us with negative velocity. So what does that mean? Are there two things? Is there something that's rotating? What's going on here? In 2016, Kathy Vivas found 22 groups that were isolated in position and velocity in the Virgo overdensity. She thought maybe only 6 to 10 of the groups were significant, but what the heck? 6 to 10 groups all in the same part of the sky? It doesn't make sense. What does this mean? It was a mystery. The mystery was solved when we got data from the ESA Gaia satellite, which measures very accurate positions of stars in the sky. So accurate that we can measure the tangential velocity of stars moving across the sky, and so combining that with our radial velocities, we could get 3-dimensional velocities, and we also had 3-dimensional positions, and so we could trace the orbits of these stars through time, and we found out they were on very similar orbits. So all of these groups were not 2 things, they were not 6 things, there's only one thing. This is a simulation that was made by my graduate student, Tom Donlin, who was an undergraduate student as well at Rensselaer. And we're going to stop this simulation at several places and show you just the stars in the simulation that have stopped with respect to the galactic center. So there are some stars that will be going out, and then it has to stop, and then it has to come back in, and where the stars stop is what we call a shell. So here we go. It goes through the center, it disrupts completely. You have stars going out in every direction on radial orbits. It's now been like 2 billion years of the simulation, and you see shell structure. So there are like 3 shells. They're very distinct. And so we're up to 3 billion years. We're going towards 4 billion years. At 5 billion years, we'll stop it again. And now we have maybe 6 or more shells. I'm not sure how many because there are getting to be so many of them. And if you go for more time, then it's 6 billion years, 7 billion years. At 8 billion years, you're going to find that the shells are all so close to each other, you can't even really tell them apart. And it just looks like big blobs out there. And so we tell from this that if the galaxy has been merged with the Milky Way for more than about 5 billion years, you don't see that distinct shell structure. So let's take that simulation that Tom made, and we're going to look at stars that are close to us in the simulation. So over here, you see that there are some with positive velocity moving away from us, going towards the shell, and some with negative velocity coming towards us, away from the shell. And if we go out further where the shell is, then we find that there's just a smooth distribution of stars. And normally, if we see that in the halo, we would have thought that that was just an equilibrium distribution of stars all going in random directions. But we know that in this simulation, they were all coming from one dwarf galaxy, so they're actually all moving on that same radial orbit. In the real data, we saw stars moving away from us with positive velocity and towards us with negative velocity. If we went out further, again, we saw this distribution. We would have said that is just a smooth, randomly directed stars in the halo, but we now know that that could be just from one radial merger. In fact, many of the stars that we thought were just randomly directed in the halo might all be from one or maybe a few radial mergers that make up most of the stars in the halo. So let's go back and pull out the stars that are on the Virgo overdensity and the Hercules Aquila cloud. So if we take just the stars we know their positions and velocities very accurately, and then we take only the stars that are on the shell, so they're not moving with respect to the galactic center, and plot the number as a function of distance, we find there's 1, 2 shells in the Hercules Aquila cloud and 1, 2 shells in the Virgo overdensity. So it must be a more recent merger than 5 billion years. And now we're going to plot, if we put stars at those shells and we imagine sending them backwards along their orbit so that they go back and forth through the Milky Way's center. We have one colored curve for each of the shells, and we look for places where the stars from the shells were at one time all in about the same place. And there are 5 places in the last 5 billion years where all the stars in all 4 shells would have been in about the same place. But we also want all of the stars in the shells to have been going all in the same direction. And there's only one of these that they all going the same direction, this red one at about 2.7 billion years. And so that leads us to believe that this merger, that this dwarf galaxy fell through the galactic center 2.7 billion years ago, and the stars have been going back and forth through the center and making these shells for that past 2.7 billion years. The bottom line is, the Milky Way is a dynamic place shaped by infalling dwarf galaxies that are pulled apart to make the stellar halo. The disk and spiral structure of the Milky Way is also shaped by infalling dwarf galaxies. While tidal streams from dwarf galaxies that came in on a more circular orbit have been studied for 2 decades, shell structure that was created from a dwarf galaxy that fell through the center of the galaxy was discovered here at Rensselaer just last year.